Hi, guys. I hope things are going great for you at home. I hope that things are going well in chemistry also. I just wanted to let you know that if you feel like you're behind or you've gotten a little overloaded, you can always reach out to me and let me know what's going on and we can work on that, okay? So today we're going to do guided notes along with calorimetry. So if you go to your thermochemistry um, folder, you can access the guided notes and follow along. You can do them side by side if you want. Remember that if you take the top tab and you pull it to the side on your Chromebook, it will give you a split screen and you can follow along as we go through this. We're only going to do the first half of this today, and then we'll do the second half next Tuesday. So today we're going to talk about calorimetry. And what is calorimetry? So calorimetry is the precise measurement of the heat flow into or out of a system for chemical and physical processes. Now remember, we have already talked about what the system and the surroundings is. Remember that the definition that we're using for a system is whatever we are focused on, right? So calorimetry is basically measuring that heat flow and what is happening to it, if it is going into the system and out of the system, and how much heat flow there is. So in calorimetry, the heat released by the system is equal to the heat absorbed by its surroundings. You remember that this is the law of thermodynamics. Energy cannot be created nor destroyed. So if the heat is being released by the system, then that means the surroundings is absorbing that heat. On the flip side of that, if the heat is being absorbed by the system or going into the system, then that means the surroundings is releasing that heat. That heat just doesn't appear or disappear. It's either going into the system and out of the surroundings, or out of the system and into the surroundings. It's going one way or the other. To measure this, we typically use an insulated device, and there's all kinds of insulated devices. We can do it all the way from something homemade to a very sophisticated insulated device, and we use that to measure the absorption or the release of heat in the chemical and physical processes, and that is called a calorimeter. Sorry about that, calorimeter. All right, so this is what a typical calorimeter looks like. This is a very simple calorimeter. You can see that it has a thermometer that is recording temperature. Typically in this type of calorimeter, we will record temperature in Celsius, because you know that we live in Celsius in chemistry. And it will record the temperature as the chemicals react in water. Whatever is your reaction mixture over here, typically it's something put in water. It's also in, this is your system right here. So it is recording either the absorption or the release of heat. So the heat content of a system at a constant pressure, that's very important, the constant pressure, is a property called enthalpy. And we show enthalpy with a capital H. On Earth, enthalpy and heat are used interchangeably. So when we say heat or we say enthalpy, that means the same thing. But we are assuming that it is at constant pressure. At constant pressure, the equation that we're going to use for that looks very similar to the Q equation, but delta H, so hopefully you guys remember and already know that when you see the delta right there, that means change in enthalpy equals a negative mass times your specific heat times delta T, which is change in temperature, equals the Q of the system, equals the negative Q of the surroundings. Remember, if the system is absorbing the heat, that means the surroundings is giving off the heat. Anytime you have a negative delta H, that means your equation is exothermic. Anytime you have a positive delta H, that means you are endothermic. So exothermic means that heat is being given off by the system and it's going to give you a negative delta H. Endothermic means that it is absorbing heat, so the delta H, the change in energy, is going to be positive. All right, so let's look at a sample problem. We're going to do 2 or 3 sample problems. When 25 mils of water containing 0.025 moles of hydrochloric acid at 25 degrees Celsius is added to 25.0 milliliters of water containing 0.025 moles of sodium hydroxide at 25 degrees Celsius in a foam cup calorimeter, a reaction occurs. Calculate the enthalpy change in kilojoules. Now right here, this is important, kilojoules. Remember that kilo means 1,000, so kilojoules means 1,000 joules. During this reaction, if the highest temperature observed is 32 degrees Celsius. So we're going to assume the following. 1, the density of the mixture is 1.0 grams per milliliter. So if we have 25 mils of water with the hydrochloric acid and 25 mils of water with the NaOH, we're going to have to add those mils together. So we're going to have 50 mils of solution. And if we're assuming that it's 1 gram per milliliter, that means you've got 50 grams. And the specific heat of water is 4.184 joules per gram Celsius. Notice this doesn't say kilojoules. So at some point, we're going to have to change this answer into kilojoules. Right here, we have it in our C, or our specific heat, is in joules. All right, so step 1, we're going to list the knowns and the unknown. What do we know? We know that the specific heat, or the C, of water is 4.184 joules per gram Celsius. We know that our volume, or our final volume, is the volume of the HCl, right here, our 25 mils of HCl, plus 25 mils of, right here, of NaOH. So we're going to add those together. 25 plus 25 is going to give you 50 mils. So your final volume is 50 mils. Your beginning temperature, or TI for initial temperature, is 25 degrees Celsius. Your final temperature is 32 degrees Celsius, which should tell you that your delta T is what? 7. Good job. All right, so now step 2 is we're going to solve for the unknowns. First, we're going to calculate the total mass of the liquid, which we did. We said it's 50 grams because 50 mils equals 1 gram per mil, 50 grams. And then we're going to calculate delta T. So TF plus TI, 32 minus 25 gives you 7 degrees. Then we're going to use the values for mass, C of water, and delta T to calculate for delta H. So delta H equals negative MCAT. So negative 50 grams times 4.184 times 7 degrees Celsius is going to give you negative 1,463 joules. But here's the deal. Now, the question asks for the answer in kilojoules. Remember that kilojoules is 1,000 joules. So 1.463 joules is going to equal 1.5 kilojoules, or 1.463 kilojoules. We divide this number by 1,000 to get to our answer. I just wanted to remind you guys that I do have Zoom office hours at 11 today if you have questions or need help. We're going to keep doing these practice problems, and I will keep working with you. All right, so now we have the same kind of question. When 50 mils of water containing 50 moles of hydrochloric acid at 22.5 degrees Celsius is added to 50 mils of water containing 50 moles of sodium hydroxide at 22.5 degrees Celsius in a foam cup calorimeter, a reaction occurs. Calculate the enthalpy change in kilojoules. Assume the following. We've got the same density. We've got the same specific heat. Step 1 is to list your knowns and your unknowns. So you're going to do that for C. For your volume, there you go. Volume 1 is 50. Volume 2 is 50. Add them together, you get 100 milliliters. Your initial temperature was 22.5. Your final temperature was 26.0. And your density is 1 gram per mil. Then you're going to calculate and solve for the unknowns. So the first thing you're going to do is change that mass from mils to grams. You've got 100 grams. Then you're going to calculate for your change in temperature. So 26.0 minus 22.5 is 3.5. Then you're going to plug your numbers into the delta H equals negative MCAT. So negative 100 times 4.184 times 3.5 gives you 1.64.4 joules. Negative 1,464.4 joules, and you have to divide by 1,000 to get 1.5 kilojoules. All right. So now what I want you guys to do, that's the end. That's where we're going to stop for today. We will stop there today. We're going to stop there today. And on Tuesday of next week, we will do the second half of this lecture. It should be about the same amount of time. I miss you. I hope you're doing great, and I'll talk to you soon. Let me know, email me, or ask for a Zoom call, and I can go over any questions that you guys have.